In this exam style question, I'm going to go through a full question that covers most of the concepts you need to know for exponential functions. So you have something to the power of t, so you immediately think this is exponential. So the temperature T of a cup is given by this function, where T is measured in Celsius degrees and T is in minutes. So it's quite important to know what your variable represents here, because sometimes they might ask you things in hours or more than that. So T is in minutes. The first question is to sketch the graph. So it's a sketch, not an accurate drawing, because it's an exponential function. So three things you need to be aware of with exponential graphs is the behavior. So is it increasing or decreasing? The y-intercept and the horizontal asymptote. So all of these can be noted from the GDC calculator. So if you graph this function, you can note all of these values. So I'm going to first find them, and then we're going to check using the GDC. But in an exam or a test, to save time, just use the GDC and just make sure that they make sense. So first, the behavior. The behavior really relies on the value of the thing being raised to the power and the power. Let's define our variable. So this is our a, so a is 2. And then k is whatever is being multiplied to this a, which is 60. So k is 60. And then c is whatever is being added. So either it's to the left or to the right, added or subtracted. So that is 18. So c is equal to 18. Now the behavior relies on a and the power, as I mentioned. So because a is bigger than 1, so we have that a is bigger than 1. So we are thinking it's going to be an increasing function. So as a graph, it's going to go like this. However, because the power of t is negative, it's going to reflect. So it's going to be a decreasing behavior. So we can confirm that it's a decreasing behavior. So decreasing. Again, the behavior is easily spotted using a GDC calculator, so just rely on that. The y-intercept is the coordinates. The y-intercept is the coordinate 0 and then k plus c. So you have 0 and then k plus c. So that's 0 and your k is 60, or c is 18. So 60 plus 18, that's 78. So that's your y-intercept. The horizontal asymptote is always y equals to c, and that will be y equals to 18. So if we are going to graph this function, we can, sketch this function. We'll need to define all of these properties. So the asymptotes, the intercept. So if I define, or if I label this to be my y-intercept, so 78, and let's say this was my horizontal asymptote, 18. Remember, this is a sketch, so it doesn't have to be accurate, but obviously 78 has to be above 18. So this could be my horizontal asymptote, and I know that my graph has to go through the y-intercept, and then go to the 18, but never touch it. So it's gonna do let's start from here. So about, I know I'm starting from the positive going backwards. The whole point is to show that it is decreasing. So usually you would start from the negative and then decrease to the positive. But on the stylus, it's just better to go from that direction. So roughly this is what it should look like. And you can check your answer using the GDC. So if I go to y equals, I'll type in 18 plus 60, and then bracket 2 to the power of negative x, and then graph this. It won't show much because my scale is 10 by 10. So if I change the window, so notice how it says from t from 0 to 10. So if I go to zoom and window, I'll change my graph, let's say from 5 to 15, just to see all the values. And I know that my y goes up to quite a big value. So let's say my maximum is 80, and my minimum could be a negative 10. So let's just check the formula and let's change the window again. So we have these values. Let's pick a scale of 2, say, and let's go even further in the y. Sorry, it wasn't it. I meant a -5. So it is having this behavior. And if I want all the values, you could go to second and then graph, and that will give you a table. So you're actually going to table. And for 0, you can notice that your y-intercept is 78. And as you're increasing in your x values, notice how they just get close to 18, and it's not actually 18 here, it's more rounded. But the values just get close to 18, but not actually touching 18. So just be careful with this. It's a rounded value. So we are roughly correct. So you can decide all of these properties using the table instead of just finding them. For part B, write down the temperature of the coffee when it is first served. So first served, remember, always deals with initial, the beginning. All of these things mean that your t is equal to 0, your variable is equal to 0. So you're going to substitute 0 in here. So you're going to get 18 plus 62 to the power of -0. And anything to the power of 0 is 1, so you're going to get plus 60, so that's 76. Sorry, 78. Which is your y-intercept usually. That's where it initially starts, and then it just goes. Part C asks you to find the temperature after 5 minutes. So since t is in 5 minutes, I can just immediately substitute 5 in there. And actually just writing this down would guarantee you a few marks. Plus 62 to the power of -5. And you can just use your calculator for this. Either show the value or of overall, or just write the calculation down. So if I go 18 plus 60 and then 2 to the power of -5, I'm going to get 19.875. And make sure you write the units down. So 19.875 0.875 degrees Celsius. Part D gives you the temperature, but it wants you to find the time that would give you this temperature. So actually, there's a specific T. It's like giving you the y and you need to find the x. That's the whole point. And this is equal to 40. And so in order to solve it, you'll first have to simplify. And you first need to deal with the c value first. So we're going to subtract 18 from both sides. And we're going to get 62 to the power of -t. And then that will be 22. Okay, and then we need to get rid of the 60, so I'm going to divide by 60 on both sides. And that's going to give me t to the power of -2, which is equal to 60 divided by 2. So you simplify this. I would recommend you keep it as a fraction, just so that's going to be easier to do the next step. So this will be 11 over 30. Now, to find t, you won't be able to do it unless you use what we call logs. The process of using logs will always be the same in any exponential problem. So if you have something like this, it could be in this order, it could be in the other order. For example, 11 over 30 equals to 2 to the power of -t. In any order that it's in, you're always going to take, you're going to use a log, which is a button on your calculator, the log of whatever is on its own, so on the other side of the equal, not the power raised. So 11 over 30 divided by the log of anything that's being raised to the power. So because 2 is being raised to the power, then it's divided by log to the power of 2. And it applies to any other thing. So if I have 3 to the power of x equals to 400, then I'm going to take log of 400 over log of 3 to be able to find the value of x. So it's always in this order of log 400 and then log divided by the log of whatever is being raised to the power. So once you've done this, this should be equal to negative t. Please be careful that we're dealing with negative t. If it was a positive t, then you just put a positive t in there. So plugging this in your calculator, we could try it here. You could go log, which is the button here, 11 over 30 divided by log of 2, and you're going to get a negative 1.447. So negative 1.447 is equal to negative t. If I divide both sides by negative 1, I'm going to get rid of the negative sign, so I get this answer. So t is equal to 1.447 minutes. For the last part, write down the temperature of the room where the coffee is served. Give a reason for your answer. So this is more of understanding what the question is and what this formula is. So when coffee cools down, and this relies on your understanding of physics. So when the coffee cools down, it releases its hot temperature to the room, such that eventually the temperature of the coffee or whatever is warm is the same as the temperature of the room. If the coffee was warmer than the room, then it would release as much of the hot energy to the room just to make us balanced. And so that's how it works, the equilibrium sort of behavior. So it means that the coffee will eventually reach a temperature that's similar to the room, which is, as you notice here, 18. So this is the reason you could give. So 18 could be the temperature of your room, and I'm not going to write it in words, but in words you could say, well, as the time increases, the temperature of the coffee gets to 18 and it stays there, which means it has the same temperature as the room.